Hi children, today's chemistry topic is structure of benzene. Benzene, it was isolated by Michael Faraday in 1825. In this video, I am planning to do the elucidation of the structure of benzene. So it follows 4 different steps. So first step, the molecular formula of benzene, it is C6H6. And the second thing, under suitable conditions, this benzene, it can undergo the addition reaction with chlorine, hydrogen, ozone, etc. In these reactions, when we are conducting with benzene, these addition reactions, it results the formation of addition products. So that indicates, you studied that addition reactions, it is possible in the case of double bonded or triple bonded compounds. That means in the case of unsaturated systems. So when we are doing this addition reaction with benzene, that means these all compounds. First you have to be add chlorine with benzene. Next you have to be add another reaction, hydrogen with benzene and ozone with benzene. All these reactions, it indicates that there is an addition occurs. That means it indicates this benzene, it is having the double bonds. And not only that, there is a 3 double bonds in benzene. That we got it from the reaction with the ozone. Benzene, when it reacts with ozone, it forms triozonide. Why it is forming the triozonide? Because there is a 3 double bonds, it's there in between. That's why it forms triozonides. So due to this addition reactions, it is confirmed that C6H6, that means benzene, it is having the double bonds. Why we are saying that there is a 3 double bonds? Because of the fact that the reaction with the ozone, it is forming triozonide. Triozonide means why it is forming tri? Because of 3 double bonds. Okay, then you understood now why it is having double bonds? Because of the fact that because this benzene undergoes addition reactions. That's why we understood that there is double bonds and 3 double bonds in that because of this ozone reactions. Okay, so double bond, that understood. The third point, even though benzene it is having 3 double bonds, it does not answer the usual test for unsaturation. We studied in the case of alkenes and alkynes. When we are adding the bromine water or bromine in CCl4, due to the sudden addition reaction with the bromine, this double bonded compounds or triple bonded compounds, it undergoes addition reaction, and this bromine it is used up for that addition reaction. That's why the color of the bromine solution, that it is orange red color, that it is decolorized immediately. That is the test for unsaturation we studied. If there is a double bond or triple bond, when we are adding bromine water or bromine in CCl4, there is an immediate decolorization if it happens, that it indicates the compound contains double or triple bond. So, when we are trying to conduct this addition of bromine with this benzene, there is no immediate decolorization. That means bromine does not use up for this addition reaction. You know that there is a double bonds here in this benzene. Then also the bromine, when we are adding, there is no chance of decolorization. Or bromine in CCl4 when we are adding, that time also you can't see the decolorization. So you can understand that this double bonds in this benzene, it's not same as that of the double bonds in the case of this alkenes. Okay, so this reaction, it is indicating that the double bonds in benzene are different from the ordinary double bonds of aliphatic compounds. Benzene, it is said to be aromatic compound. Alkenes, alkynes and all we are saying about, it is aliphatic. So the double bonds in this benzene, it is having the difference from the ordinary double bonds of these aliphatic compounds. Then one more case we can say. Under ordinary conditions, this benzene, it undergoes substitution reactions. Substitution reactions means, you know that what it is substitution. Instead of one, another will come. Right? So when you conduct the chlorination, so what happens? C6H5Cl will formed. How? This C6H5 you can write it as C6H5H, then Cl2 you can write it as ClCl. So instead of this hydrogen, this chlorine will becomes here. That means replacement. That means substitution it is possible to occur. Like saturated compounds. We are doing this type of substitution reaction in the case of aliphatic compounds, that it is in the case of this CH4 and all. Right? Why? Because of the fact that this CH4 it is an aliphatic saturated compounds. Here single bonds only. That means one of the H from this CH4 it is replaced by this chlorine. So CH3Cl plus HCl it is formed. Right? So saturated compound situations we discussed about the substitution reactions. Okay. So that type of substitution reaction it is possible to see in the case of this C6H6. So from this you understood that in the case of benzene there is a double bond. If there is a double bond, then also does not shows the unsaturation test. That means the double bond it is different from the ordinary aliphatic compounds. Then also it is the benzene, just like saturated compounds, it is having the substitution. So surely you know that the benzene it is different from the ordinary aliphatic compounds. Right? Then benzene was further found to produce one and only one monosubstituted derivative. Here are written. Benzene, when it undergoes the substitution reaction, it forms only one monoderivative. Monoderivative you can see. That means monosubstituted derivatives it forms. It also indicated one another thing. That means this C6H6 means you know that it is having 6 carbon atoms and 6 hydrogen atoms. Yes. So when it is forming monosubstituted derivative, that indicates all the 6 carbon atoms and all the 6 hydrogen atoms of benzene are identical. That indication it is given by this monosubstituted derivatives of this benzene. Yes, so from this reaction, they understood that all the carbon atoms and all the hydrogen atoms of the benzene ring are identical. Yes, on the basis of this observation, Benzene-Kekule in 1865 proposed one structure. Kekule, the scientist name it is Kekule. That's why it's the Kekule proposed one structure for benzene. That structure we are calling the name is Kekule structure. His name is Benzene-Kekule. In 1865. Yes, so in his proposed structure, the benzene is having the cyclic arrangement of 6 carbon atoms. Cyclic arrangement of 6 carbon atoms means C, 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 C. Then, okay, 1, 2, 3, 4, 5, 6. Cyclic arrangement of 6 carbon atoms with alternate single and double bond. When there is a double bond here, then single bond, then double bond, then single bond, then double bond. Likewise. And one hydrogen atom attached to each atom, each carbon atom. In every hydrogen carbon atom, there is one hydrogen. This is the Kekule's proposed structure. So what's the structure? Cyclic arrangement of the carbon atoms. And in the carbon atoms, when we are arranging alternate single and double bond, and next thing, all the carbon atoms having the hydrogen atom. Then otherwise we can write like this. The structure it is. This benzene, it is having unusual stability and unique properties, and also it is a stable molecule. Then also there is certain limitations of this Kekule's structure. The first one, the presence of 3 double bonds here. We think that because of these double bonds, this is very much reactive towards the addition reactions. But this benzene does not follow the addition reactions, but it behaves like saturated compounds, saturated hydrocarbons. That's why it is doing the substitution reactions. So that is the first limitation. This benzene does not follow the addition reactions even though it contains the double bonds. Then it behaves as a saturated hydrocarbons. That's why we can say that the Kekule structure cannot explain the peculiar behavior of the double bonds in benzene and also its unusual stability. And the second one, the Kekule structure contains 3 single bonds, CC single bonds, carbon-carbon single bond, and 3 CC double bonds. And the normal bond length of the CC single bond is this one now. So 1.54 Armstrong, that it is 154 picometer. Okay. And that of double bond, it is 1.34 Armstrong, that it is 134 picometer. But experimentally, it is found that all the CC bonds, even it is a single bond or double bond, experimentally it is found that all the carbon-carbon bonds in benzene of equal length. Its value, it is said to be 1.39 Armstrong, that it is 139 picometer. So that value, just look into here. This single bond length, it is 1.54 that we are expecting. The double bonds, the length we are expecting, it is 1.34. But what the value you got it? All the CC bonds, even it is a single bond or double bond, you got the bond length, it is 1.39. What is the indication? That means the bond length of this CC bonds in benzene, it is in between the single and double bond. And the third one, according to Kekule structure, we are expecting 2 isomers of 1,2-disubstituted benzene. This is the structure. That means the Kekule structure indicates, this is the Kekule structure, right? This indicates the possibility of 2 isomeric 1,2-dichlorobenzene. So here 1,2, here also 1,2. But when you think, you can see in one of the isomers, the chlorine atoms are attached to the doubly bonded carbon atoms. But in the case of here, the chlorine atoms are attached to the singly bonded carbon atoms. However, benzene was found to form only ortho disubstituted product. Here or here, that's not a matter. It forms ortho disubstituted. Ortho means adjacent positions. Okay, the ortho disubstituted product, that thing only it is indicating in the product's case. So this problem, the position, double bond or single bond, that problem it can be overcome by Kekule by suggesting the concept of oscillating nature of the double bonds in benzene. Oscillating nature means how? Oscillating nature means either you can draw the benzene like this or this way. So when it is like this, ortho disubstituted product, it's not a problem. Wherever the ortho product it is coming, that's not a matter. The double bond, single bond, that problems it will not becomes. Yes. So these are the 3 limitations. First one we said about that benzene ring, it is having the double bonds, then also it is preferring the substitution reaction rather than the addition. And next one we said about that the bond length of all the carbon atoms in the benzene ring, it is identical. Then the third thing, the isomers, the ortho, whether it is a single bond or double bond, the adjacent, the positions of the substitution, it is forming ortho disubstituted product, that is having the importance. That's why the Kekule suggested the oscillating nature of the benzene. Even with these modifications, the Kekule structure of the benzene fails to explain the first one, unusual stability. And the next one, the substitution is occurring rather than the addition reactions. These 2 concepts he explained with the help of resonance. Why this benzene it is having the unusual stability and why it is occurring the substitution reaction rather than the addition reaction, that two concepts, it is explained later by resonance.